Hey guys, welcome to the video. Today I'm going to talk about nitration. Nitration is a type of electrophilic aromatic substitution reaction. Now let's say we have a benzene ring and we want to form a nitrobenzene, which is like this. Right. Now here, benzene ring, which is aromatic, and it does not want to lose its aromaticity, and this is resonance stable. So to be able to make this a nucleophile, you have to make sure that the electrophile is strong enough or more electron poor, or you can say more electrophilic, so that the attraction between the nucleophile and the electrophile is enough to force this reaction to happen to make nitrobenzene. Now, the two important things that you have to remember: benzene, this will be acting as our nucleophile here, and we have to somehow make a positively charged nitro group that will be acting as our electrophile. Because if we can make sure that we have a positive charge on this nitro group, that means which is much more electron deficient and more electrophilic, and the possibility of benzene acting as a nucleophile will increase. Now, to make sure that we somehow produce this positively charged nitro group, we add nitric acid to sulfuric acid. So nitric acid, the structure would be something like this. So we have an oxygen that is charged, negatively charged, and we have a positively charged nitrogen, and we have an uncharged oxygen here that is connected to hydrogen. Now we have our sulfuric acid, where we have a sulfur atom, central sulfur atom, that is connected to 4 oxygens, and 2 oxygens are connected to 2 hydrogens here. Now when you mix them together, you might actually think that okay, it has a negative charge here, so it has electrons to give away, so probably this will pull this hydrogen away. By the way, sulfuric acid is actually stronger acid than nitric acid, because the conjugate base, which is this HSO4 minus, which is much more stable, resonance stable than the nitric acid, the conjugate base of this nitric acid, and that's why that's why sulfuric acid actually can give away a proton and much more acidic than nitric acid. So nitric acid in this particular case will act as a base, which sounds weird, but that's actually the case when you mix nitric acid to sulfuric acid, because sulfuric acid is stronger than nitric acid. Now you might think that okay, it has negative charge here, so this will try to pull away this hydrogen atom, this bond will break, and the electrons will be left on this oxygen atom. But it happens a lot, probably, because this actually happens a lot in the reaction, probably, but the problem with this is that this proton transfer is reversible. That means even after this happens, the resulting compound will try to reform the nitric acid again and again. But once in a while, what happens is that the uncharged oxygen of the nitric acid will try to pull away this hydrogen. This bond will break and the electrons will be left on this oxygen atom. Now what we will form is that we will form a very small amount of positively charged nitro group. How? So the mechanism is just like this, just how I showed. So now we have this oxygen here, we have a positively charged nitrogen, we have this oxygen with negative charge on it, and now this uncharged oxygen from before is connected to 2 hydrogen. Now it has only 1 lone pair electron and already a positive charged. Now this bond will break and the electron will be left on this positively charged oxygen atom. Now it will form water and will leave, and we get water from here, and we have this negative charge. We will try to form a double bond here, and now we have this positively charged nitro group, and which will be our electrophile in case of nitration reaction. Now we have our electrophile. Now we already have a positive charge. That means that it is a strong electrophile. That means it is much more electron poor. Now our benzene can act as a nucleophile. So we have our benzene. I probably don't know how to draw benzene properly, because every time I draw benzene, I don't know why it looks like that. I suck. But anyways, we have our benzene, right? And let's say that we have somewhere we have this nitro group. Now this double bond, one of the double bonds from the benzene ring, I'm sorry, will attack this positively charged nitrogen atom, right? Because this is electron poor nitrogen atom. And then we will form an intermediate where our double bond, this particular double bond, will break. So we'll have positive charge here. We'll still have double bonds here and here. And we'll have this nitrogen that is connected to 2 oxygen atom and already has a positive charge. And you can see that this particular carbon atom is already connected to a hydrogen atom. I'm just drawing it so that it will be easy in the end to explain that why we what's happening with this reaction. Now this structure, this intermediate structure, actually has other resonance structures. That means it can go back and forth, and this positive charge, let me change the color, this positive charge is spread over the atoms within this benzene ring. Because you see the aromaticity is lost temporarily, of course, because in the last step we will reestablish the aromaticity, because benzene does not like to lose its resonance stability and the aromaticity and all those things. But so this positive charge will be spread over the atoms, the carbon atoms, you can see like within the ring. So this double bond will try to so this double bond, the electrons will move here, right? Let me draw a little bit clearly. Okay, so we have our red color, and okay, so the electrons will move there. So that means that the positive charge will now move here, right? And we already have hydrogen and our nitro group from before. Okay, now here, and the next resonance structure will be, now these electrons will move here, and we have our resonance structure which looks like this, and the positive charge will move here, and we have the same thing as before. Right, so that means this positive charge, that means that this positive charge is spread over mostly, or you can say that this positive charge mostly is spread over 3 atoms within the ring. You can see, right, just as I drew here the resonance structure, and we call this resonance structure sigma complex. And you have to draw these resonance structures in the exam when you were told to draw the mechanism. Now from here, you can see that we already have this resonance structure, let's say, and we have water in our reaction system. So we have oxygen atom, which is connected to hydrogen atoms, which is water, and we have lone pairs of electrons. And this will, let me change the color. This will go here like this and try to pull this hydrogen away, and this bond between this carbon and hydrogen will break, and the electrons will be used to reform the double bond where we had the positive charge. So now that means we have one oxygen atom that pulled away the hydrogen atom, right? And we have a positive charge on this oxygen atom. That means H3O plus. You all have seen this before. And our main product that we have been waiting for is this nitrobenzene that we formed here. So we had this reformed double bond here. I'll just change the color so that you understand. So we reformed this double bond here, and we already had double bonds here and here. Let me redraw it properly. Okay, so this is our benzene ring. We already had these two bonds, and we reformed this bond here, and we have our desired nitro group that has a positive charge on it. So, or we can also write this like this. So this is our nitrobenzene.